I'm sure this is a familiar scene if you live in a crowded metropolis like me. This is going to be a tight squeeze. Oops, I think I have hit something. I don't think the damage could be that bad. How do I know? That's what the chemistry of collisions tell me. Let me tell you all about it. Hello and welcome to a high-impact discussion on chemistry. Today we will be talking about the collision theory and the factors that affect collisions. We will end the show by cracking exam questions in Exam Decoded. When I was first introduced to this topic as a student, I was very intrigued. I pictured loud explosions and high-impact accidents and wondered, what does chemistry have to do with collisions? But then my teacher told me something that I am going to share with you now. You already know that all the phenomena that we see around us occur as a result of chemical reactions. Did you also know that each of these reactions occur due to collisions between particles like molecules and atoms? In effect, everything that you experience in the chemical world is a result of collisions. So, studying the nature and behavior of collisions is absolutely essential to the study of chemical reactions. In 1916 and 1918, two scientists by the names of Max Strauss and William Lewis put forth a collision theory to qualitatively explain how chemical reactions occur and why reaction rates differ for different reactions. According to this theory, reactant particles are assumed to be hard spheres, and these particles must collide for a reaction to occur. Another very important postulate of their theory was that not all collisions result in a chemical reaction that yields products. Only a fraction of the total collisions have the energy to connect effectively. Wondering what this means? Let's move to a place where you can study collisions more closely. That's right, I am talking about a bowling alley. Let's see what it takes to knock these pins down. Pay close attention to the path of the ball as well as the meter, which shows you the momentum of the ball. In the first case, we see that the bowling ball is thrown with average momentum towards the pin. But since its aim is not very good, the collision fails to make a big impact. In the second case, the aim or orientation of the ball is absolutely correct, but since it is moving very slowly, it too fails to drop the pin. Now in the third scenario, the aim is perfect and the momentum is high. Finally, it succeeds in knocking over the pin. It's not so easy to bring about collisions that yield desired results, is it? This is why we classify all chemical collisions into two groups, effective and ineffective collisions. Those collisions which result in chemical reactions and yield products are called effective collisions. If no reaction occurs, then such collisions are called ineffective collisions. Now, what makes a collision either effective or ineffective? If you think back to our bowling example, you could tell that both the aim as well as the ball's momentum needs to be optimum to knock down a pin. Similarly, for an effective collision, both the orientation of the particle as well as the energy with which they collide must be optimal. Let us look at a few specific examples to understand this well. Nitrogen dioxide reacts with carbon monoxide to produce nitric oxide and carbon dioxide. As you can see, the first three orientations yield no results as the orientations of the molecules do not facilitate the formation of products. But look at the orientation in the fourth scenario. The particles are perfectly aligned to form the resultant products. Now let's look at the reaction between nitrile chloride and nitric oxide, which gives nitrogen dioxide and nitrosyl chloride. Here is what a successful collision looks like. We see a nitric oxide molecule approaching a nitrile chloride molecule in the correct orientation. This leads to the formation of nitrogen dioxide and nitrosyl chloride molecules. But if we were to change the orientation of either nitric oxide or nitrile chloride, what do you think would happen? That's right, no reaction would take place. So we have seen that only if the two reacting molecules approach each other with the correct orientation will a reaction take place. Otherwise, there will be no reaction. I am sure these examples would have shown you how important the orientation of particles is in order to have an efficient collision. How about helping me solve this question based on that? Ethene and hydrochloric acid react to form chloroethane. And there are 4 possible ways in which the HCl molecule can approach an ethene molecule before collision. As you may have gathered, only one of these orientations of the reacting molecules can lead to a reaction yielding the product ethyl chloride. Guess which one? Keep thinking and I'll give you the answer when I return after the break.